Hey guys, last week we talked about how to solve a system of equations using one method, which we called the graphing method. Today I'm going to teach you about a different method called substitution. To begin, let's look at an example. Here are a couple different equations where we've got different shapes equal to different shapes, and my goal is to figure out how many dots each of those shapes is worth. So if a circle and two squares and a triangle has the same value as 4 circles and 1, 2, 3, 4, 5, 6, 7, 8 dots, well, how much is a square or a triangle worth? Now, the key is that in each equation, a triangle is always worth the same amount, and squares are always worth the same amount, and circles are always worth the same amount, and I need to make all three of those equations true at the same time. So, why don't you hit pause, play around with it a little bit, and when you're ready, let's reconvene, and I'll show you how we can use some concepts to make some progress. So, give up already? Oh, let's see what we can do. I see in this equation that 2 squares is equivalent to 3 circles, and I see down here in this bottom equation that I've got 2 squares. And so if I were to maybe swap them, take those 2 squares out and replace them with 3 circles, then I see that I've got a total of 4 circles on this side and a total of 4 circles on this side, and I can get rid of 4 circles from both sides, and I find pretty quickly that a triangle is worth 8 dots. So maybe I'll write that down here. One triangle is equivalent to 8 dots. Using similar logic, I can take the 2 squares out of this top equation and replace them with 3 circles. And that means that one triangle, which I could replace with 8 dots, or just the number 8 for simplicity, 8 dots is equivalent to 1, 2, 3, 4 circles. Therefore, each circle must be equal to 2 dots. Almost look like little smiley faces. And if I do a few more replacements or substitutions, I can see that down here I must have 6 total dots, and to be equal, each square must then contain 3 dots. And I've solved this. I figured out that a triangle is worth 8, a square is worth 3, and a circle is worth 2. So, the substitution method takes advantage of this new way of thinking about solving problems by swapping things that are equivalent. The steps for this substitution method might look a little complicated at first, but I think once you've seen a couple examples, you'll find the substitution method is extremely repetitive and routine and the same over and over and over again. So, first step is to try to get a variable by itself. Like in our last example, we were ultimately able to figure out the triangle by itself. Then we substituted that into some of our other equations. A little note there is that when we make these substitutions, we'll have to use parentheses. Then we can solve that equation to figure out the value of one of our variables. And once we know the value of one of our variables, we can substitute that into our original equation to find the variable, the other variable. So let's see this in action. First example says to solve the equation 3x plus y equals 5 and 2x minus y equals 10. Here's my first hint for the substitution method. The book problems always come with the 2 equations written right on top of each other. For the substitution method, it's actually much more convenient and easier if you spread them out, write them next to each other like this, so that you've got more space to work. So, first step is I want to try to get one of the variables in either equation by itself. So, I'm either going to work to try to get this x by itself, this y by itself, this x by itself, or this y by itself. In this particular system, there's a clear choice for me, and that is I'm going to try to get this y by itself because there's no multiplier in front of it. which means I'm not going to have to divide by something, and I probably won't have to deal with any fractions. So to get this y by itself, I'm going to choose to subtract 3 x's from both sides of this equation. That gives us the equation y equals negative 3x plus 5. So that's step 1. I'll switch colors each time so you can see the different steps. Step 2 says to substitute that expression into the other equation. I like to draw a circle around this value and then an arrow from that into the other equation, and specifically I'm going to put it into the y of the other equation because after all we just found what y was equal to. So the substitution step says to rewrite this equation, but instead of y, I'm going to put in parentheses negative 3x plus 5. That will look like this: 2x minus, and then in parentheses, negative 3x plus 5. And then everything else stays the same, equals 10. That's step 2, the substitution step. Notice that in this equation, now there's only one type of variable, x's, which means we can do our normal tricks to figure out what x is equal to. That's step 3, which I'll use a different color for. So to solve this equation now for x, the first thing I'll do is use the distributive property and distribute this minus sign through. Minus negative 3x is the same thing as adding 3x's. Minus 5. And then the 2 x's in front here can drop down. That's still equal to 10. I'll probably combine these x's. Minus 5 equals 10. And to get x by itself, I think I should add 5 to both sides. And finally divide by 5, and we get our first answer, that x is equal to 3. There's one major difference between the substitution method and the graphing method, is that when we use the substitution method, we find the variables one at a time, whereas with the graphing method, we find both of them at the same time by looking where they intersect. So step 4 then is to take this number 3 and substitute it into this equation. So again, let me switch colors. I'll take x and replace the x in this equation with the number 3. I want you to notice this loop of a circle, an arrow goes to this equation, you do some work, and that comes back up and gets put in this place. The substitution method always looks like that. You can bank on it. You can give yourself, 4 or 5 lines worth of space, and every problem will have this kind of arrowed loop look to it. It's very consistent. So if we take the x out and replace it with 3, we get the equation y equals negative 3 times 3 plus 5. That's all there is really to step 4. And then step 5 is simply to evaluate that and figure out what it's equal to. So let's do purple. Final step here, negative 3 times 3 is negative 9 plus 5. Negative 9 plus 5 is equal to negative 4. And so this suggests that our answer is the combination 3 and negative 4. And I didn't write it in here, but we can always check this to make sure it works. If we plug in a 3 for x and a negative 4 for y, in this first equation we get 9 plus negative 4 does equal 5. That's true. And over here, if we plug in a 3 for x and a negative 4 for y, that's 6 minus negative 4, which is the same thing as adding 4. 6 plus 4 does in fact equal 10. So that combination works. You may circle these two numbers as I've done here, or you may write it in the ordered pair fashion of 3, negative 4 either answer is acceptable. So let's look at one more example together, and we'll run through these steps with a little less explanation each time. So first thing, isolating a variable. I'm going to choose this x this time to isolate because there's no multiplier in front of it. So I'll add 4y to both sides. That gives us x equals, you can write -1 plus 4y or 4y minus 1. It really doesn't matter. Step 2 now, the substitution step. I'll put a circle around this expression and draw it in over here for x. That gives me 2 groups of 4y minus 1 plus 2y's is equal to 3. And step 3 now is to solve this. 2 times 4y is 8y minus 2 plus 2y equals 3. And I can combine the y's to give me 6y minus 2 equals 3. I'll add 2 to both sides, and 6y is equal to 5. That's starting to scare me a little bit. Maybe this example doesn't have nice numbers. I have a fraction, 5/6 for our y value. And if we continue, step 4 is to take this number and substitute it back in over here for y. That gives us 4 times 5/6 minus 1. 4 times 5/6 is the same thing as 26 minus 1, or 26 minus 6/6 would be the fraction 14/6, which can be reduced to 7/3. So I've got a potential answer, x equals 7/3 and y equals 5/6. Again, I'm a little nervous because usually my examples work out cleanly. So let's test this. I'll get out a calculator. Since it has all those fractions in it, it might be easier to use a calculator to answer. So I'm going to take the fraction 7/3 and store it into the x variable using the stow key and the letter x. And then I'll take 5/6 and store it into the y value. And though it took me a second to do that, now I can evaluate these really quickly by just typing 2 and x plus 2y, and I'm hoping that this gives me a 3. Ooh, it doesn't. So I don't need to bother checking the other one. I know I've got a mistake. Let's see if we can go back and see what happened. Adding 4y's to both sides, that looked okay. I made a substitution over here, copied it correctly. So I see 8y's minus 2 plus 2y's, and when I combined them I wrote 6y's. That really should be 10y's. So let me switch colors and write in a few corrections. So instead of 6y, this should be 10y, which means I should have divided by 10. And it still works out to be a fraction, but at least it's not as ugly. 5/10 is the same thing as 1/2. And if I plug in 1/2 over here, 4 times 1/2 is 2. 2 minus 1 is 1, and so that suggests an x value of 1. Let's test that instead. We'll go back to our calculator and store 1 in for x, and store 1/2, or the decimal point 5, in for y. 2x plus 2y. Notice this time it gives us 3, like it's supposed to. And if we type in x minus 4y, hopefully this gives us a -1. It does, and so we're finished. So there's the substitution method, and also an unexpected example of what to do when something goes wrong. So that's it for today. Tune back in a day or two when we talk about the elimination method, which will be similar with a little bit of a twist to this substitution method.